Okay, thank you for the invitation. Thank you to the conference organizers for the invitation and for giving me an opportunity to present some of our recent work here. So I will speak on some recent work we have done in nictite superconductors and looking at evidence of superconducting and magnetic fluctuations present above as well as below TC in these crystals. This is the work of my PhD student who has just completed his thesis, Biplab. And the crystals are from a group in India. They have been working on making single crystals, and these are the references of their crystals. We have also worked with another group in TIFR for cobalt doped calcium iron arsenide single crystals, Tamizabel and Dhar. The funding is from the Department of Science and Technology, India. So, maybe it's working. So in nictite superconductors, the phase diagram is quite complex and rich. There is an antiferromagnetic-like ordering in the system, and this is as a function of doping. So as you dope the system, this is iron arsenide, barium iron arsenide 1 to 2 compound, which is cobalt doped. As you increase the doping, you will find that the magnetic correlations in the system decrease. The antiferromagnetic ordering in the system decreases, and there is an onset of superconductivity at beyond some value of doping concentration. Superconductivity emerges inside the system. Apart from that, the system has other features. Not only is there magnetism and superconductivity present inside the system, but as you dope the system, there is also a structural transition inside the system. You go from a tetragonal to an orthorhombic phase inside the system. And this is related to other interesting effects where the orthorhombic distortion, as it goes into the orthorhombic phase, the orthorhombic distortion is small, but there is a significant anisotropy in the transport. The resistivity in the A versus B plane becomes very anisotropic, and this has been related to pneumaticity in the electronic state of the material. And there are these pneumatic order which has been shown. Herman in the beginning of the conference showed nice data on pneumatic order inside these nictite superconductors, and these fluctuations can extend up to the overdoped regime. So you have, apart from that, there are other interesting effects which have been observed. For example, you have this antiferromagnetic ordering temperature as well as a superconducting ordering temperature, and it appears that both of them shift as you change the iron isotope inside the system. So you can see that both the superconducting transition as well as this antiferromagnetic ordering transition, both of them, as you change the isotope, there is an effect on both of them, and this has been seen in different type of these nictite superconductors, which gives the impression that magnetic ordering and superconductivity might be in some way connected in these systems. Apart from that, there have been observation that inelastic neutron scattering have shown that deep inside the superconducting state, there is loss in energy. There is a loss peak that we find deep inside the superconducting state, and this peak actually survives to well above TC of the superconductor. And these have been associated with magnetic fluctuations which can be present deep inside the superconducting state. There have been other interesting observations relating to the superconducting gap in different nictite superconductors. If you see the superconducting transition, the superconducting gap actually has a tendency, in some of these nictites, it has been observed that it survives slightly above TC. It can exist slightly above TC. This is in the cobalt doped iron arsenide superconductor, where point contact spectroscopy evidence has shown that there is some evidence that it is surviving above the TC of the superconductor. So there have been all these different issues which are related to magnetism and superconductivity in these nictite systems, and perhaps there is a competition and interplay between magnetism and superconductivity in these class of materials. So I will be basically interested in the cobalt doped iron arsenide superconductor. And the type of question that we would like to ask is, what does actually doping do to the nature of magnetic order which is present inside the system? What is the real effect of doping? And do magnetic correlations survive in some way above the TC of the superconducting state in these systems? So do magnetic correlations, and what is the form of those correlations? And if magnetism and superconductivity are in some way connected to each other, then if magnetic correlations survive above TC, is there any evidence of any superconducting fluctuations also existing above TC? So these are the type of questions that I will be asking, I will be interested in asking. So for this work, we have actually looked at 3 different classes of single crystals. One is, all of them are barium iron arsenide with cobalt doping. One of them is underdoped with a lower TC. The TC is about 18 Kelvin. One of them is optimally doped. It has the highest TC amongst this class of crystals which were prepared, which has a TC of about 27 Kelvin, which is sitting here. And in the overdoped sample is about, again, 26 Kelvin. So all these 3 different crystals, one is in the underdoped, optimally doped, and overdoped single crystals. We will investigate what are the features that we see in these 3 single crystals. They will be typically, the nomenclature that we follow is the CO10, which is underdoped, CO14 is optimally doped, and CO20 is in the overdoped regime. If you look at the resistivity as a function of temperature, CO14 and CO20, both of them, you can see a good, nice resistivity transition, a transition in the resistance. And you can see the shift in the TC. CO14 has the highest TC, CO20 and CO10 have lower TCs compared to the optimally doped sample. All these 3 samples, if you measure the magnetization as a function of temperature, they have a robust superconducting signal. This is, all the 3 samples have a very nice Meissner signal, and you can locate the TC in all the 3 samples. The hysteresis, you can now also measure the hysteresis and magnetization. And the hysteresis and magnetization, it shows the usual hysteresis, a very robust hysteresis. There are some features which, if I have time, I'll get back to here from the end of my talk. But the idea is that you can see that these single crystals have a robust superconducting state, conventional behavior which has been reported. We have measured the JCs, and the JCs are equivalent to what have been reported in literature for these crystals. Now, this is the optimally doped sample. You measure the magnetization as a function of temperature, and you can measure it in low magnetic fields, and you can increase the magnetic field. You will see that there's vortex penetration inside the superconductor. The diamagnetic shielding response decreases. Now, as you approach the TC of the sample, the diamagnetic response monotonically decreases, and in conventional systems, this should actually flatten out. However, if you expand this, and so this is the expanded portion of this, magnetization as a function of temperature, what you find is that the magnetization crashes, but then it does not become 0. It becomes positive, and then it has a long tail. The magnetization is very small, but the magnetization, instead of going to 0, it becomes positive, and then it continues for a very long temperature window. This is, TC is around 27 Kelvin, and it is continuing up to maybe 70, 80, or 90 Kelvin. So this is the positive magnetization response that appears. It changes from a diamagnetic, it goes into a positive signal, and then it has a long tail. Furthermore, as you increase the magnetic field, you will see that this signal gets stronger and stronger. All these measurements which I'm showing are in the zero field cooled state. You can see similar effects in underdoped as well as in the overdoped regime. though the effect is smallest, I mean the effect is smaller in the underdoped and the overdoped regime, it is the strongest in the optimally doped sample, which has the highest TC. It's present in both of them. It's a very small signal, but if you compare the two, I will show you the comparison later on. The effect is the strongest, turns out to be strongest in the optimally doped sample. So we were actually puzzled, what is this effect? Why does it go from a diamagnetic to a paramagnetic signal, and then it has such a long tail which extends over a very long temperature window? So for doing this, this is our own magneto-optic setup. You basically image the magnetic field distribution, incoming beam of polarized light, and it undergoes a Faraday rotation, and you look at the intensity of the Faraday rotated light across the sample, and you will see an intensity map which looks like this. Wherever there is a high intensity, it corresponds to larger local field, and wherever there is a lower intensity, that corresponds to a weaker local field. So, so this is the conventional magneto-optics, but we have some variant to it. And essentially what you do is that you come in with a polarized beam of light, and you actually have a Faraday rotator. This is something we have built, a very compact Faraday rotator which oscillates the polarized beam of light. And then you actually capture the images synchronously as the polarization is rotated. And this gives you high sensitivity for imaging. The original idea was from Wingarten, and we sort of made a compact version of it, and it works well. So we use this to actually image this positive magnetization state very near TC and above TC. And what do we see? So this is at 220 Kelvin. This is roughly about a millimeter wide. You don't really see much. In your magneto-optical image, there is almost no contrast in the image. This is at 220 Kelvin. Field is very, very low. It's actually about 0.2 Gauss. And if you take a line scan across it and measure the local field as a function of distance, there is almost no feature that you see across this line. But as you start cooling the sample and you reduce the temperature, what you find is that suddenly there is a positive magnetization. You can see a strong intensity, a bright intensity which develops in the sample. And then as you keep on cooling the sample, the intensity becomes more and more positive. This is, if you measure the local magnetic field BZ across each of these regions, minus H, that is proportional to the vertical, that's proportional to the magnetization. And you will see that this feature that you see in your magneto-optics is corresponding to your magnetization going positive as you are reducing the temperature. So this is where we saw that there was a positive magnetization which is sitting above TC. It has this sort of a feature. Now, if you take this positive magnetization and plot it as 1 by T, you can see this the same, one of these curves is plotted as 1 by T. You see that there is a Curie-like behavior. So it may seem like it's a paramagnetic-like system. The magnetization or the susceptibility is 1 over T, and it has this sort of a feature. However, if you go into one local region, and in magneto-optics it allows us, our system allows us to do that, is that you measure the local magnetization and you do a magnetization hysteresis measurement, then at high temperatures, at 72 Kelvin and above, you see that your magnetization as a function, the local magnetization, Bz minus H, as you go up and down in field, has this sort of a feature. And as you reduce the temperature, you see that there is an opening of the hysteresis loop. And then as you go to lower temperature, it becomes wider. This is all above TC. This is all above TC, that you have this local magnetization, and this magnetization, as you increase the temperature, it's not a paramagnetic-like behavior, but its hysteresis loop vanishes. This sort of hysteresis has been known and seen in small nanomagnetic systems, which is called the superparamagnetic effect, where at low temperatures the magnetization is stable, but as you increase the temperature, the magnetization starts flipping around, and you can go from an open hysteresis to a to a hysteresis which looks like this. There's no hysteresis left in the system as you warm up the sample. And this is characteristic of systems which have short-range magnetic order. So what we think is that what we observe above TC is that there is evidence that in this system you have some sort of short-range magnetic order which is present inside the system. Now, okay, so there might be local regions with short-range magnetic order which is present, and we wanted to know that, okay, so to investigate and image these regions, what we did was that we did a differential measurement, basically to see how much is the shielding in the sample. You modulate the external magnetic field by 1 Gauss, and you check that in your sample, where are the regions which respond with field and where are the regions which do not respond with field, okay, or have very weak response with field. So you modulate an external magnetic field. There could be magnetic regions which are responding strongly to the field, and there could be other regions which are not responding so strongly with the field. So we wanted to look at their distribution. So we did this differential imaging. And if you are at 70 Kelvin, the green region corresponds to regions which are responding to an external field modulation, and the yellow regions are those regions which are responding more strongly to an external field modulation, and the dark regions are the regions which are not responding strongly to magnetic field. These are shielded regions. Okay, so there is regions where you have strong magnetic response which have these magnetic features, which have positive magnetization features, but wherever you have these features located very close to them, you have these regions which are strongly shielding. As you reduce the temperature, you come down from 70 Kelvin, you start seeing that these become more and more stronger. You have these yellow regions which have this response to the magnetic field, and sitting very close to them are these regions which have strong diamagnetic shielding response. As you go below TC, the response changes to a completely diamagnetic response, but you have regions with positive magnetization which are surviving along with the system. So the superconducting state just below TC or reasonably below TC is not a very homogeneous state. It still has superconducting and magnetic fluctuations which are sitting along with the system. But here above TC, we think we have evidence that you can see response of magnetic fluctuations which are surviving along TC, along with superconducting fluctuations. To see whether there is actual superconducting fluctuations which may be present above TC, we did a resistance versus temperature measurement with field and without field. So if you have local puddles of superconducting order which are present above TC with a strong magnetic field, you will suppress them. And if you take the difference in the conductivity with and without field, if there was no superconducting fluctuations, it should go to 0 at TC. This is plotted as T by TC. But if we did it for our data, you can see that there is excess conductivity which is present well above TC. This excess conductivity indicates that there excess conductivity may be arising because of presence of superconducting fluctuations. The zero field resistivity data can also be analyzed to get conductivity as a function of redefined temperature, and this goes by the Larkin-Aslamazov theory, where the conductivity as a function of temperature above TC, if there are Cooper pairs fluctuations which are present above TC, you should see enhanced conductivity. So this is the Larkin-Aslamazov line, and you can see that the conductivity is actually still higher than this line. So there is some evidence of superconducting fluctuations which are present above TC. These are present very close to regions where there is magnetic order present inside the system. So your magnetization plotted as a function of 1 over T has this Curie-like behavior, but the behavior here is really of short-range magnetic order. There are regions with short-range magnetic order which gives rise to this sort of a response. And in these regions where you have this sort of a local magnetic order, you see that around the regions where you have local magnetic order, you have superconducting diamagnetic fluctuations which are present around these regions. If you pick up the value of the magnetization at this point, and you plot it as a function of this mu b by a dimensionless unit, you will see that the CO14 sample, the optimally doped sample, which has the highest TC, has the strongest effect of magnetic fluctuations. The value of magnetization turns out to be the strongest. This is all above Tc, it's strongest. And then the magnetization actually bends over from this behavior. Instead of crossing along this line, it bends over because there is diamagnetic fluctuations. Because of the onset of diamagnetic fluctuations, the magnetization does not follow along this line, but it bends off until it drops into the superconducting state at Tc. So here it is all magnetic fluctuations. Here there is an onset of diamagnetic fluctuations along with Tc. Along with magnetic fluctuations, there is onset of superconducting fluctuations which suppresses the magnetization, and it falls into the superconducting state below Tc. So we propose that a phase diagram where you can go from high temperature, there is an onset of magnetic fluctuations, which is in this blue region. It enters into a region where there are superconducting and diamagnetic fluctuations until it reaches into the coherent superconducting state below Tc. And the orange region is the sliver over which there is an coexistence of magnetic and superconducting fluctuations. We have shown how this behaves for all the three samples. We can measure the superconducting fraction also from this magnetization data. And if you look at the superconducting fraction for the sample above Tc, for the sample which is the optimally doped sample, which has the highest Tc, the superconducting fraction, the fluctuations that you see above Tc are the largest. It is smaller for the underdoped sample and smallest for the overdoped sample. And similarly, the sample which has the highest Tc is the optimally doped sample, also shows the strongest magnetic fluctuations. So it appears that magnetic fluctuations may in some way be actually aiding in superconductivity, and there may be a correlation that the sample which has the highest Tc also shows the strongest effect of magnetic fluctuations. The patterns that you see here have been seen earlier because of twin boundaries, where the earlier work of Bina had actually shown that along these twin boundaries, below Tc, the diamagnetic fluctuations or the superfluid density is strongly enhanced along these regions. In these samples also, we feel that along these regions, there might be an enhancement of superconductivity as well as magnetic fluctuations, which are stabilized around these regions. This is all above Tc. And of course, it leads also to an inhomogeneous state below the sample. I don't have time to actually get what happens. There are other interesting features which happen below Tc regarding vortex penetration and so on, but I'll just show one piece of data that as you go to the overdoped sample, you can actually see conventional penetration of vortices, normal bean-like profile, and the system becomes almost conventional. As you enter close to the optimally doped sample, you start seeing all these effects where you see a coexistence of these magnetic-like fluctuations along with superconductivity. It's not completely suppressed, but it is still present. We had seen earlier in calcium iron arsenide similar sort of effects where there is magnetic fluctuations along with superconductivity above Tc. So the summary is that with doping in these nictite samples above Tc, you lose long-range order, but you may be preserving some short-range magnetic correlations inside the sample. Along these regions, around these regions, as you cool the sample, some superconducting puddles are being nucleated, which start growing, and as they grow, they start growing until you go below Tc, and you have your superconducting state in which there are these small magnetic inclusions which can survive inside the system, and perhaps these two are related to each other. They might be aiding each other in giving rise to superconductivity. This is the superconducting volume fraction, and these are the magnetic fluctuations. And this is the summary. I just leave it at this point.
Thank you very much. So, questions?